Swayam Prabha. Digital India. Educated India.
Hello everyone. So, in the last session we have discussed the radiant heat protective tester, then horizontal flame protective tester and vertical flame and radiant heat protective tester that we have used. Now, from these instruments we can get the flame protective performance value. So, flame protective performance studies using horizontal flame protective performance tester and vertical thermal protective performance tester, okay, test as per the standards ISO 9151 and NFPA 1971. This is as per those standards. Fabrics are placed in horizontal and vertical orientation that we have already discussed. So, maker burners and mass flow controller. So, those are used for the flame protective tester and data acquisition system and propane gas cylinder and copper calorimeter. This is used for flame protective tester. Okay. And propane gas is used for flame exposure. And flame protective performance, if we see, it is basically empirical equation related to cumulative heat. Okay. The G is the cumulative heat and T is the time. Now, you can see the heat flux is actually given by this equation mc delta T absorptivity, A is area and delta T is the time. You can see that mc delta T A and delta small t is the mass of copper calorimeter, m is the mass of copper calorimeter, specific heat C, okay, and temperature difference between final temperature and initial temperature, and it is in Kelvin, area of copper calorimeter and thermal difference. Okay. So, time difference between the final time. So, this is the time difference. So, from there we can calculate the heat flux, and second degree burn time of clothing is determined by the intersection point of two curves, Stoll curve and experimental curve, that I have already we have discussed here. This is the intersection point which gives the second degree burn time. Now, we will discuss another development. Now, we can see this is the second degree burn time and which is used in the Stoll curve. This is the T Stoll temperature. So, from this equation we get this is the standard Stoll curve which is developed for the thermal rectangular heat flux exposure ranging from 4.2 to 16.8 kilowatt per square meter. So, that is the range where we can get, and this is the Stoll curve. T is the time exposure and T0 is the original time. So, original temperature of skin or sensor in this case. So, from there we can develop derive this equation, and looking at this standard instruments are fine, that vertical or horizontal which is tested in a particular orientation, but the limitation is here either fabric should be in the vertical or should be in horizontal plane. So, but our human body and our activity not necessarily is always keep the fabric in only in the either in horizontal or in vertical orientation. So, for that it was thought that okay, can we have one instrument which will be able to test the fabric at any angle at a time. Even a heat can the heat be from the top side. So, in the flame can be from and fabric is at the bottom. Can it be at this any angle, any known angle. So, that heat can come through this where fabric orientation is at certain angle. So, with this idea another instrument was developed which has been patented, where the it is called multidirectional thermal protective performance tester. Now, let us see here the first let us see the video of this equipment. This instrument was developed in house and this was actually displayed in one of the international exhibition. Now, this is the instrument here. You can see this instrument here the and totally it is controlled by computer and it is self ignition is there and we can start and stop the flame and it follows the STM F72 F2703, STM F2700, NFPA 1971, ISO 17492. So, these standards we it follows. Now, you can see here now the instrument is now it is opened. Now, here again there we can create the moisture there inside. Now, here the this is the fabric holder. Fabric holder and on the other side it is a copper calorimeter is there. Now, you can see here this is the radiant heat source and these are the burners. Okay. It is connected with the computer and there is a gas is connected for and now we can see that it can be rotated. It is not it is a very slowly you can rotate and we can set at any angle known angle. So, if we want suppose now I can show you, suppose we want flame and radiant heat to be from the from above. In that case we can set the instrument in this fashion. Now, if we set it it will be in the vertically it is moving projected from the top and if we try to if we set in other direction now you can see here that can be controlled. You can see this instrument, see it is there. So, like see now here in this situation it is totally that heat is coming from the bottom, that is it has come downward. So, if we try to test in this direction, or maybe in any other, in this direction we can test, any direction we can test. Okay. We can stop the instrument in this fashion, in this direction. So, depending on the, and it has been observed that direction, effect of direction is actually significant on the thermal protective performance. Now, we can see here automatically it is getting fire and self ignition is there. We can change the intensity here, depending on our requirement we can make the combination. Now, these are the data, initial data we have to some feel that what is our fabric type and all this fabric code. Now, the fabric is being, sample specimen is being placed. This is the sample holder. Now, fabric sample is just placed, very quick, very easy method of clamping. We can simply clamp the fabric here, and then the copper calorimeter is placed. We can change the distance also. Now, through the computer control we can run the instrument. What type of data we want, what type of flame we want, what is the intensity we want. So, everything can be controlled. You can see here, now it is a flame, now it is both flame and radiant heat is exposed. At fabric is at vertical direction, we can test it in any other directions. So, here the data will be collected and that will be analyzed. Thermal protective performance is analyzed here. So, different type, all the data we get, we can analyze the thermal protective performance. Now, this equipment can be installed in the department. In our department it has been installed in IIT Delhi and running satisfactorily, and further modification and optimization is going on for the performance. The main innovations are newly developed machine is close to reality, and as it simulates structural fire outbreak. So, in the structural fire outbreak, fire can come from any direction. So, that the important, only the vertical and horizontal orientation is okay for certain to some extent to get some value, but if we can get the TPP rating at any multiple direction, at least some important directions, that will give us more realistic result. Test can be done at any angle with a variable angle. Test can be performed at various intensity of convective and radiative heat. We can make combination, and the technology which has been developed here, exposure of radiative and convective heat at any possible angle with respect to gravity, okay. And heat transfer is through combined convective and heat radiative heat mode. So, that any combination we can make here. Materials other than textile can also be evaluated for any other material, any planar material can be tested in this instrument, maybe building material can be tested here. And next one is the thermal mannequin. This is actually we have developed our clothing, then it is tested with on standard laboratory the thermal mannequin testing. You can see here it gives us 3-dimensional heat flow. This is our developed fire protective clothing, and now this is tested in our standard lab, and it was tested and data were analyzed. Now, you can see the different layers of fire protective clothing. If you see here, this is the skin, okay, and which releases sweat, and thermal liner is there, and if it does not absorb moisture or sweat, it will remain within the within this, it will remain within this layer. Okay. So, then it is a thermal liner, which is basically insulating layer, and then moisture barrier layer, which allows moisture to move out and prevent any liquid or chemical penetrate inside, and then outer shell. Now, see, you can see the heat is getting reflected or it is prevented here, and you can see here the fire, it is fire protective, fire does not allow the fire penetrate, and then the water particle, it penetrates through the outer shell, but it is prevented at the moisture barrier layer. Okay. The 3 layers, outer layer as a fabric are used, 3 layer fabrics are usually used, outer layer or shell layer, this is the shell layer, and you can see here it is flame is being prevented at the shell layer, but moisture vapor can come out from the body. Middle layer or moisture barrier layer, and inner layer thermal barrier, and heat transfer phenomena, it is basically heat transfer through clothing or fabric, heat transfer through the air gap, and heat transfer through the human skin. So, there are different layers through which heat gets transferred. Now, the importance of fire protective clothing, you can see this is the body, human skin and air gap, and then the heat protective clothing. So, heat is getting transferred from the fire, from the heat source, trying to get it transferred through the human skin, but the protective clothing, its function is to prevent the heat, stop the heat transfer. So, maintain a barrier to isolate the wearer from the thermal exposure. So, this the wearer's human skin or human body should be isolated from the heat source. That is the function of the fire protective clothing. It traps air between the wearer and the barrier. So, air, it will try to trap the air between the wearer and the fire or any heat source, and it reduces the burn injury, provides high protection time, so that one can perform his duty and then come out of the fire. So, protection time is very important. So, the main requirements are high heat resistance. So, it should not get melt, or it should be it should retain its structural integrity. It should not get flamed or get fire easily. So, high limited oxygen index LOI value and high abrasion resistance. If abrasion resistance is less or tear strength is less, then the outer layer will get destroyed and then fire can penetrate inside easily. And one most important thing is low toxicity of gases released. It has been observed that in case of fire, the majority of the incidents of death are not due to the heat, but due to the toxic gas release. So, we have to have certain material so that it should not release the toxic gas. And high tensile tear and seam strength. So, during the activity there should not be any damage in the clothing. So, that is very important. We have to be very careful in maintaining this. Okay. And next module is that now here we will continue with the different standards for extreme heat protective clothing. So, we will try to discuss the standards which are being used. Now, heat and flame resistance testing is done through by following different standards. So, thermal protective performance. So, what is that thermal protective performance rating as per NFPA, okay, 1971, the TPP rating equal to burn time. Burn time TPP rating is burn time in second by incident heat flux. Okay. So, calorie per centimeter square second. So, that is a TPP rating, calorie per centimeter square, and LOI as per ASTM D2863. So, digital oxygen index apparatus. So, that can be used to calculate the limited oxygen index. Then TGA analysis, thermogravimetric analysis, where we want to get the idea about the weight loss or gain due to the heat exposure. So, here the samples are heated from the room temperature to high temperature like 600 degrees Celsius at a rate of 10 degrees Celsius per minute. So, that at the rate the heat is increased, and then we measure the change in weight, okay, or loss as it is heated. So, gradually when it is heated, the weight loss is measured. Then ACM, scanning electron microscopy, we use to get the idea about the samples before and after burning, what is their structural changes, that we try to get idea. Now, there are different international standards. Let us try to see, and these standards have their specific application, specific heat exposure, okay, that we can see at a particular use we can. So, ISO 9151 standard, where the heat exposure is 80 plus minus 4 kilowatt per square meter. So, this is actually only flame type exposure. Here it is a flame exposure. ISO 9151, it gives only the flame where the one maker burner with propane gas is used, okay, and methane gas, propane or methane gas supply. So, one maker burner which is used, and typically it is in a vertical direction, fabric is kept in horizontal direction, and the sensor is copper disc calorimeter, and this is mainly used for firefighters, industrial workers. So, for this application we can use ISO 9151, and the sample size is 14 by 14 centimeters in the square shape. Then ISO 6142, these standards talk about only the radiative heat transmission. So, there are 3 levels of exposure. One is low level of exposure is 5 to 10 kilowatt per square meter, medium level it is ranging from 20 to 40 kilowatt per square meter, and high level exposure is equal to the flame 80 kilowatt per square meter. So, that is the ISO 6942, and here the heating source is silicon carbide, okay, 6 silicon carbide heating rod is being used for to create the radiative heat, and here calorimeter dimension 50 millimeter by 50 millimeter, that is the dimension, and thickness 1.6 millimeter. So, that is a standard dimension, and it is also used for firefighter exposed to low to high heat flux. So, here it is not fire, it is a heat flux. So, that is from the distance when the firefighter works. So, it is exposed by radiant heat. For those type of application, those type of firefighter clothing we use ISO 6942, okay, and the specimen size is 23 centimeter by 8 centimeter. And another ISO standard which is ISO 17492, and that standard talks about the combination of both 50% convective, that is a flame, and 50% radiative, where the heat flux is 80 kilowatt per square meter. That is the high level of exposure, but 50-50. So, here what we do, we use 2 maker or Fisher burner as we have used in our developed equipment, okay, and it is fixed at 45 degree from the vertical, and 9 quartz T500 infrared tube. So, that also is being used in our instrument. So, what we tried to develop the instrument as per ISO 17492, that is the instrument which we have already seen in our last module. The copper disc calorimeter is used, the diameter 40 millimeter diameter, and thickness again it is a 1.6 millimeter thickness, and here this is used for emergency firefighter exposure. So, where the firefighters are entering into the fire scene, in those case we can use this in ISO 17492 standard, and sample size is 15 centimeter by 15 centimeter square. Okay. Here you can see the label ISO 9151 is only radiant heat, and 17492 is for both radiant and convective heat. Sorry, 9151 is for convective, only convective heat, Now, another standard which is very widely used. So, performance required for protective clothing for firemen, it is NFPA, okay. NFPA 1971 1971. So, exposure it is here it is 50% radiative and 50% flame. So, similar to earlier, but here heat flux is 84 kilowatt per square meter. In earlier case if we see in ISO it is 80 kilowatt per square meter, but NFPA says it is 84 kilowatt per square meter, and the TPP rating is 35, which is actually minimum TPP rating should be 35, and effectively we can see that it is half of this 17.5 second. It should, the second degree burn time should be 17.5 second, and that will show that minimum TPP rating is 35, and this is used for structural firefighter clothing that we can use here. And another is that ISO for performance requirement for protective clothing for firefighter, ISO 6942. ISO 6942, it is a radiative heat, just we can see, you can come back, this is the ISO 6942. Here in this table which we have discussed, this shows the type of heat exposure. Now, here we try to see the what is the level of protection performance requirement for firefighter as per ISO 6942. This is a radiative heat transfer index, which is actually for level 1. Level 1 it should be more than 18 second, lesser level 2 more than 18 second, and level 1 it should be around more than 10 second. So, that is the type of fabric requirement, and here heat flux, radiative heat flux is 40 kilowatt per square meter, and this is level 2, and level 1 is the lowest level and level 2 is the highest level of protection. So, we can see that for at that level, if we can keep the time of exposure time is more than 18 second, then its fabric is okay. Now, another is the European standard. As per European standard, performance requirement for protective clothing EN 9151, where heat transfer index HTI, its level 1 is more than equal to 9 second, level 2 is more than equal to 13 second, where heat flux is 80 kilowatt per square meter. L1 is lowest level and L2 is the highest level of protection. So, NFPA, that is National Fire Protection Association, NFPA USA, NFPA 1971, the standard for protective ensemble for structural firefighter. This is actually 1971, NFPA 1971 is for structural firefighters protection, design, performance, testing and certification. So, NFPA 1971 it will give us entire requirement, design certification will be there, performance and testing and certification, that will give everything in that. All sewing threads used in the garment should be made of inherently flame retardant fabric, flame resistant fiber. So, that is important. As per NFPA, they say that we cannot stitch the garment with the normal swing thread, it should be inherently flame resistant, otherwise the at the certain heat or fire the garment can disintegrate. Disintegrated garment will be useless. So, average TPP should not be less than 35. So, that we have already mentioned. So, 35 should be TPP rate minimum, then the fabric will the clothing will pass the standard. Tear resistance. So, it also talks about the tear resistance. Tear resistance should be more than 100 Newton, that is the minimum requirement, and outer shell layer should have breaking strength greater than 623 Newton, and heat shrinkage in any direction should be less than 5%. So, this standard talks about the shrinkage. If the shrinkage is high, then it will fail the standard. Moisture barrier and thermal barrier should not shrink more than 10% in any direction during thermal shrinkage resistance test. So, that thermal shrinkage resistance test it should pass. So, these are the overall National Fire Protection Association NFPA 1971, any structural firefighter should pass through all these parameters. And another standard is that arc flash rating. So, that is different types of flash fire. It is not normal, it is basically it is the intensity of heat is very high with a fraction of second, and it is as per the ASTM F1959. This is the standard, which is different from fire protective tester. So, here what is boundary? The arc flash boundary is defined as the distance at which the incident energy is 1.2 calorie per square centimeter, that is the boundary, arc flash boundary. So, people should work at certain distance from the actually probable incidence area where the arc flash can be can happen. Now, arc flash rating NFPA 70E PPE categories. What are the ratings? You can see here. Category 1, it is 4 calorie per square centimeter, that is the type of arc flash. So, arc rated shirt pant, face shield can be where boundary is 18 inch, that is boundary means at that distance 18 inch distance the incidence energy will be 1.2 calorie per square centimeter. Now, we can see for example, here category 1 cat 1 in arc flash labeling as per NFPA 70E, the standard that as per that standard the boundary 18 inch, okay, the boundary 18 inch for cat 1 with the where its rating is that 4 calorie per square centimeter, which refers the 18 inch refers to the working distance, that is the working distance. Boundary 18 inch means it is a working distance, the assumed distance typically 18 inch from the arc flash source, where the incidence energy calculation determines required PP like arc rated shirt, pants and face shield. So, that means at that distance it is calculated. Now, category 2 is 8 calorie per square centimeter. The arc rated jacket coverall face shield boundary is 24 inch. That means, it is a heat energy is generated is much higher, double, and the jacket and coverall what we use and face shield hoods, it should be at 20, boundary is 24 inch, and in category 3 25 calorie per square centimeter, and where full arc shoot and hood should be used with the boundary 36 inch. So, that is the different category. 1 is the low level of protection required, arc rated shirt, pants and face shields are used, and category 2 for that we need coverall or jackets and face shield, hood boundary is required, and category 3 which is very high protection requirement is that full arc suit hoods, okay, that this is the arc flash rating. It is both by NFPA 70 EPP category or ASTM category, as ASTM F1959, that we can use any of the rating depending on our requirement. And category 4 you can see heavy arc suit is required, hood, full body protection, and boundary is 48 plus inch. So, it is a category 4 is extremely dangerous. So, we have to maintain our protection. Then molten metal and flash resistance as per ISO 9185. So, the splash resistance refer to specialized protective clothing designed to shield industrial worker from molten aluminum and other like aluminum, maybe molten metal, iron. So, different types of molten aluminum and other hot metal splash by reflecting radiant heat and preventing direct contact. So, one is you have to first reflect the radiant heat, and also at the same time it should be prevented from penetrating the molten metal inside the cloth. So, that is the standard. So, aluminum splash resistance up to 100 to 150 gram without penetration, that is the standard, and for iron or steel flash it is up to 200 to 250 gram before breakthrough, and test method is ISO 9185 or EN 373, and for aluminum the classification is D1 to D3, and for iron like iron and steel it is a E1 to E3. These are the different standards or category. So, high performance fabrics, aramid or treated cotton withstand more than 250 gram Fe or iron and more than 150 gram aluminum splash. So, for this splash is very dangerous during the for industrial worker. So, they should wear proper protective garment, and as per the testing is done by ISO either 9185 or EN European standard 373. And next is the cone calorimeter test. The heat release rate, so peak value typically 200 to 600 kilowatt per square meter, it is material dependent. Time of ignition, it ranges 10 to 60 under 10 to 60 second under 35 to 50 kilowatt per square meter heat flux. Heat release rate it can measure, often 10 to 60 megajoule per square meter for textile or polymer. Smoke production rate about 0.05 to 0.2 square meter per second during burning. So, this cone calorimeter we can test all these parameters: heat release rate, time to ignition, heat release rate, the total heat release, smoke production rate. Now, let us see the military and defense heat protection. Aramid uniforms like Nomex, Kevlar with a very high limited oxygen index, limiting oxygen index its LOI value more than 28 and thermal stability up to 370 degree Celsius, that aramid uniforms are used. Ballistic and thermal composites. So, basically sometime with the fire protection, some mechanical threat also is may happen. So, dual protection is required with 20 to 30% weight reduction, okay, and it is with a lighter weight we can develop through the meta-aramid or para-aramid mixture. And flame resistant camouflage fabric we can use, withstand 3 to 5 second direct flame without ignition. And another is that that advanced coating, ceramic or carbon coating, which boost radiation. So, we can to improve the thermal protection performance, to improve the radiative heat, reduce the radiative heat transmission. So, we can coat the fabric with either ceramic and carbon. Carbon is very high heat resistant, carbon coating we can use. Oil and gas industry flame protection, for that, so arc thermal performance value, okay, measures the energy in calorie per square centimeter of a fabric that can absorb before causing second degree burn. So, that is ATPV. So, fire retardant coveralls, monocrylic blends and meta-aramid we can use. It provide arc thermal protective value of 8 to 12 calorie per square centimeter for daily wear, and multi-layer PPE system which achieve more than 40 calorie per square centimeter arc flash protection in high risk zone, that is multi-layer we can use and also antistatic and chemical resistant to prevent ignition in explosive atmosphere. So, zone 1 and zone. So, for this type of oil gas industry there is always a chance of that chemical comes or antistatic agent or explosion. So, for that antistatic finish should be there. So, that for this type of fabric should be used in oil and gas industry along with the fire protective test and standards compliance. So, certificate of NFPA 2112 is required for using the in the oil and gas industry, like in structural firefighter the standard was NFPA 1971, here for oil and gas industry NFPA 2112 or EN ISO 11612 for flash fire protection. So, here in the oil and gas industry the fire will be sudden flash fire. So, for that different types of standards are required. Now, another area where the extreme heat situation arises, that is space aerospace application. Thermal insulation layer mainly aramid and silica fabric which withstand more than 1000 degree Celsius. Basically the heat generates when the astronaut enters into the atmosphere. So, due to high friction the heat generates, it is a re-entry condition, re-entry suit is the in those in that time the person should be protected, the astronaut should be protected from the high heat. So, crew protective clothing. So, Nomex, Kevlar they are meta-aramid, para-aramid they are used with LOI value more than 28 for fire and arc protection, and flexible composites are used for high strength. So, FR fabrics in carbon or aramid laminates for lightweight high strength panel. So, that in this type of applications we can use the carbon aramid laminates also are used, and space habitat safety FR textile liners reduce the flame spread by 70% in microgravity test. So, that the special tests are required for space and aerospace application. So, for future we need different innovation. There are different innovation trends and future trends are there. So, these are the areas where it is a sustainable FR material. So, we should go for sustainable material development. So, bio based aramids are there, and green coatings are used, where green coatings are used with more than 60% renewable content, that is the green coatings. So, sustainable material, smart textiles are used. So, the after the bio based aramids, so then smart textiles. So, embedded sensors. So, with the textile we can embed different types of sensor to get real time data, either heat or maybe moisture, any other physiological parameter what is happening within the human. So, that can be monitored, and adaptive materials like shape memory polymer or phase change material these are for thermoregulation that can be used. So, that these are basically in the research, and it is also we have started using the shape memory polymer and phase change material. And shape memory polymer, what they are doing, that can be actually, that can change the polymer shape and enhance the thermal protective performance. Like phase change material actually if we incorporate within the textile, that this phase change material can change its phase from solid to liquid and absorb the heat and which prevent the heat to enter into the human body. So, that is there in the future trend, and also nanotechnology. So, nano coating and aerogels for lightweight, more than 30% improved thermal resistance. So, with the by using nano coating main advantage, it has got very high surface area, and that changes the character, that can absorb heat. And aerogel also, sometimes nano aerogel particle, if we use the aerogel contains the total the porosity is very high, and it is very insulating, and naturally it is a very light material. So, without enhancing the weight, so lightweight, it improves the thermal resistance. So, these trends will are there. So, we will discuss in detail in the next session. Till then, thank you.